here we have two former students of the University of Coruña. Well, one of them still linked, well, two of them still linked, completing their master thesis now. And, well, they're living the dream. They're working with Alan in Coruña. So, congratulations on that. And I will just leave the floor to you so that you can share cool stuff about your work with us. Thank you.
Thank you so much for the good introduction. This is my colleague, Lois Soto, and I'm Javier Garea. And as Laura said, we both work here in Coruña supporting processes at a cool company named NomaSystems that is specialized in mobile solutions, but uses Erlang as its daily basis when talking about backend stuff. So we are going to talk to you about two components or two libraries that our teams developed along the years for Erlang solutions, and I mean for Erlang-based solutions, not for companies. That we recently open sourced, and that they share a common thing, that is that they are in some way out of the most common way of solving the problem they solve, right? When we fully embrace the OTP design principles, sometimes you need to tweak a little bit your libraries in order to get an extra boost of performance. So we always recommend you to do some benchmarking on your code, test your code, and all that stuff before putting these things into production, anything in production, and especially if you do this kind of optimizations. So the first component is named NQ, and we'll start taking a look at the problem NQ solves. All right, so imagine the well-known problem of where you have a set of M producers, a set of M consumers, and you want to share data between them using a buffer. In this case, we are going to add an additional restriction, and we want our data to be consumed in the same order it was produced. We can model this by taking a set of M producer processes, a set of M consumer processes, and a FIFO queue, which is in fact an ordered buffer. When implementing this model, we have to keep in mind that we are adding two restrictions, two properties our implementation has to fulfill. The first one is that we need to avoid data races, because we have a lot of processes accessing the data, and we need to be sure that nobody makes operation based on all data. And we also need to ensure the ordering. We will be talking about a FIFO queue. So maybe the easiest way to fulfill these properties is to serialize the access to the data source. So we can model operations, transactional operations that do any kind of stuff you want, read, write a value based on that value, and all that kind of things. And if we serialize them, we are ensuring that the order is kept, and also that we don't have data races. All right, so let's go to the Erlang stuff. While a process is a native concept in Erlang, there are several ways of implementing a FIFO queue. In the recent versions of OTP, if I remember well, there's a new module named queue, where you can that allows you to create a data structure that works as a queue. But we have to remember that we want our queue to be accessed concurrently. It's not like we want to store only the value. We want our process to access it and read it. So maybe in a problem like this, what I will say is the most common go-to when talking about a shared resource where we want to serialize the operations on it and where we want to be sure that it can be accessed by several other processes is a Gen server. In fact, Gen server is like the go-to for everything. When you don't know how to implement your solution, just place a Gen server and you can go with that. So if we think about it, a Gen server perfectly fits our needs because operations are serialized by default because we have the message queue for that process, and we can store a shared resource in the state of the Gen server, and we can create these transactional operations because we are exposing an API both for producers and for consumers, and we can implement operations that do several stuff against the data source. Let's see it more graphically. Imagine that we have a postal office with a single worker that is in charge of storing and delivering packages to our producers and our consumers. As you can see, this is a model of how the Gen server works. But what happens when a lot of producers and a lot of consumers arrive at the postal office at the same time? All right, we overwhelm this work. The fact is that this single worker can't handle such an amount of requests at the same time. So this is a well-known problem. This is known as the single process bottleneck. Essentially says that a system is being constrained by the throughput of a single process. Because if we remember it, even though we have a lot of producer processes and consumer processes, all the operations are executed in the queue through the Gen server process. So even though there are a lot of consumers ready for consume data, if the Gen server is not ready to deliver the data, the system is going slower and slower. All right, imagine now that instead of a single worker, we place a locker in the postal office. This way, producers and consumers can arrive at the postal office and store or take a piece of data. But, all right, in Erlang we can model this as an ETS, but how do we know how each producer or consumer will know, how do we tell them which compartment of the locker it has to access? If you remember, I said that we need to ensure order. So we decide to use counters. Counters are incremental integers that are shared, and the point is that we are storing in the ETS these counters. We got one counter in for the producers and one counter out for consumers. So each time a producer wants to ingest data in the queue, it just updates the counter, it gets the new value, and that value is the index of the compartment where it has to place the data. In the same way, we got a counter for the consumers that is updated each time a consumer wants to retrieve data from the queue, and that update operation tells to him or her where it has to get the package. This works because the update operation, as I say, is a combination of a read and a write operation. It's an atomic version of a read and a write. You don't know the state of the counter until you update it, and at the same time updating it is writing a new value. So we are avoiding the data risk. So this is mostly how NQ works. NQ is a library that implements a solution for the problem we seen at first, and it does it by implementing some sort of locker with a ticketing system where each time a process wants to do something on the queue, it just takes a ticket, and the ticket says to it where it has to work. So you will say to me, okay, good story, is this really better than a gen server? Well, we performed some sort of benchmarks between NQ and NPQ, which is another library we also open sourced recently that implements partition queue, where each partition is managed by a gen server, and we did it in the specific case where NPQ has a single partition, so we got a gen server based queue. And as you see, it seems like the ETS concurrency pattern performs a little better. In any case, I want to warn you that, again, that you should benchmark your code before putting it into production, because in the specific case of my laptop, this benchmark does not hold. You know, M1 chip, different architecture, so keep it in mind. And that's all for NQ. I leave you with Lois.
So, hi. Do you hear me nice? Yes. So, NBSON is our library for producing and parsing BSON documents. And the interesting thing about BSON is that it uses an approach, a coding style that enforces some optimizations on the coding process. So I'm sure you all know what this is. This is a JSON file. And JSON is a data format that represents information in a human readable manner. And basically, BSON is a binary encoded JSON. So the information on the left, this is an Erlang binary, which represents the same information as the JSON on the right. And basically, as I said, BSON transforms the BSON binary into an Erlang term, which shows Erlang block lists as that representation, and transforms those Erlang terms into binaries back again on the encoding process. And what's interesting about BSON is that a BSON document has additional information, which is length and type information, that makes traversing the document more fast and parsing its values easier. So let me use an example to help you understand this. So this is the BSON we had before, and the first 4 bytes are length information. So this BSON is 36 bytes long. The next byte is the type of the first field, which, since it's a tube, this is a string field. Sorry. The following bytes until the first 0 are the ASCII codes for the key of this field. So this would be NAME, name, and a trading 0. Then, since this is a string field, we have 4 bytes for its length. So the value is 12 bytes long, which would be the ASCII codes for NomaSystems. And then we have the following field, with its type byte, which is 16. So we have a 32 bits integer, which k is h, and value would be the following 4 bytes, which is 17. So NomaSystems is 17 years old, and the trading 0. And basically, BSON decoders are all about taking parts, as I have just done, of a binary and building the Erlang representation for that document. And there are several pieces of information on the Erlang efficiency guide, which are important when we work with binaries, because they help us understand a relevant optimization on the decoding process. So I'm going to be talking a little bit about that chapter, the constructing and matching binaries chapter. And here we find that we have 4 types of binaries in Erlang. The first 2, RefC binaries and heap binaries, are actual binary containers. This means that these binaries are the actual binaries on the memory structure, either on the process heap or on a separated heap. And the other 2 types are binary references to those containers. So we have sub-binaries and match contexts. And sub-binaries basically generate when we split a binary, either with the split binary function or using a binary pattern against a binary. And match contexts are also references to binary containers, but they are optimized for the process of matching out parts of a binary from a binary. So let me again use an example, a simple use case to represent this. So imagine we have people's information, where if we have, for a person, we only have the name, we proceed that information with a 1, and if we have the name and age for a particular person, we proceed that information with a 2. It's a very simple use case. So a decoding function for this type of encoding of information could look like this. We have a decode function that takes a binary and an accumulator where we are going to be placing the fields of each person information. And each execution of the decode function takes the information for one particular person from the binary and returns it on the value variable and returns also the rest of the binary. And after that, it calls itself, putting that value, that person's information in the accumulator. So we end up decoding all the binary, and the binary ends up empty. So we execute the first clause, and we return the people information. We have to do a list reverse because I'm sure all our learners understand why we do this, but we basically, on the decoding process, we put the information about each person on the beginning of the accumulator, so at the end we have to do a reverse of that list. And basically, when the compiler looks at this function, it creates a match context for the binary pattern. So we have a match context, a binary reference, pointing to the beginning of the first parameter, of the binary in the first parameter. But because we match out the type variable, sub-binary has to be created for that type variable. So the match context moves to the following part. This process repeats as many times as binary parts we have on our pattern. In this case, we just generate one sub-binary and we move the match context to the rest 0 variable. And at this point, I have to say that generating a sub-binary or using sub-binaries, but generating sub-binaries is more expensive than updating the match context, because the match context is just a reference that we update every time we move it, and every time we generate a sub-binary, we have to create a new object, a new reference to a part of a binary. So it's better to not generate sub-binaries if we can do that. And this is what the compiler tries to do. The compiler tries to not generate more sub-binaries than needed and tries to use the match context when it is possible. And because in this case, we pass the res0 variable to a function, we are not splitting it or returning it, the match context can be reused. This means we don't have to generate a sub-binary for the res0 variable and then use it on the body of the function. We can reuse the match context. So we are going to count the times we reuse the match context, and at this moment it's 1. So we are going to take a look at the getPerson function, which implementation will be this one. And again, we split a binary using a binary pattern, and the match context moves to the last variable as we saw before. But in this case, we are returning in both classes of the getPerson function the rest variable. So the match context can be reused. We are not going to add another unit to our counter. And that's it. That would be our implementation for this simple use case. When the NVSON decoder was implemented, we took inspiration from JSON, which is an Erlang library for decoding and encoding JSON. And on the decoding implementation of JSON, we saw that they use it, they reference it on the README, a particular programming style that, in the particular case of decoding binaries in Erlang, it enforces the usage of the match context, of the subbinary delayed optimization, which is the fact that we are reusing the match context. Because we are delaying creating the subbinary and we are just using the match context. So this particular programming style is CPS, the continuation passing style, that is based on the idea of using functions that, don't return a value, but call to the following function on the program flow, making explicit how the program flow should continue. So this is a little bit tricky to understand. So let me again show an example of the decoding function for the use case we had before, but using CPS. As you can see, the CPS decode function does not call to getPerson and expect for that getPerson function to return and do something with the return value, but just calls getPerson, making explicit in the case of if we have a 1 for a particular person, it makes explicit that the program flow should follow in a manner that we only take the name from the binary. And if we have a 2, it makes explicit by the second parameter of the getPerson function that we have to take both the name and the age. So this would be a CPS implementation of the decode function. And as you can see, as it happened with the decode implementation I showed before, the rest variable is pointed by the match context. This is the last part of the binary pattern, and it's passed to the getPerson function. So we reuse the match context. We are using the subbinary delayed optimization. So we add a 1 to the counter. And the getPerson function, because after getting one person information, we call CPS decode again, because we are going to take the type for the the number for the following person. The getPerson function calls to CPS decode, passing the last part of the binary that it received. So that binary is pointed, that part is pointed by the match context. The rest variable is pointed by the match context. And we are again reusing it. So we are reusing it twice. This is a very simple use case. So the opportunities for reusing the match context and using the subbinary delayed optimization are limited. But if for more complex program flows, like the one on the decoder for an actual JSON, where we have more than 15 types of fields, I think, the program flow is much more complex, so we have much more opportunities to reuse the match context. So you might, watching this or seeing this implementation, you might think that CPS is more complicated than the style we are all used to. It is indeed coupled to the program flow. And even in some cases, it can be a threat to the call stack. But as I said, in the particular case of decoding binaries in Erlang, it works. And we made some benchmarks for comparing our implementation of the decoder with the Conti Home Bison Erlang library, which implements the decoding process using the direct style, which is the style most Erlangers are used to. And we obtain an increased performance on that decoding process for several sizes of documents with bisons on them. So again, as Javier said before, we are not, before using CPS, you should make some tests and ensure that they actually represent an improvement for the performance of your particular use case. But for us, it worked. And that's it. If you found our solutions interesting, make sure to visit our repos. Thank you for your attention.
Thank you. I have a question. Is the first library you presented us in Q has any kind of persistence for the Q?
No.
Okay, thank you.
In fact, the information is stored in the ATS, so you got that layer of persistence. You know, if the system goes down, you lost everything. If I remember well, we had different implementation, variation of what NQ is, and instead of using an ETS, it uses files and store things in disk. But you know, reading from disk is slower than reading from memory, so it's slower. And if somebody's interested in this kind of solution, you can ping us and we may open source it.